temperature effect.
Yeah. Okay. You just summarize a little bit,
Okay.
and then words. I think it's also long enough. Okay, so I
think you can skip a little bit the introduction.
Yeah, I didn't do like 1 second. Yes. What I showed already during my talk. So this is the approach. We're talking about proximity effect and seeing the Josephson effect regarding the Majorana topological superconductivity. And of course, this also I showed. And the key point here is when when you have the parity protection, your periodicity of the Josephson current become from 2 pi become 4 pi. And the very common measurement we do is called this Shapiro step measurement. So you radiate the system with the RF signal, and then you see quantized steps in your DC voltage measurement. And then if you have, well, ideally, if you have a topological state, which is 4 pi, and you get double the size of the steps. Okay, and that's firstly been measured in the system of this mercury telluride, and they see this quantum spin Hall state, and then they measure this Shapiro steps, which is the indication of the 4 pi. And that's, I think at the moment, that's only people saw that's the only explanation. Majorana is the only explanation for this. And then very soon, okay, well, not soon, after a couple of years, we start to realize there's some other side effect. You can have this fake state. Most prominently is this recently, the group published something themselves saying if you have wrongly designed circuits, especially a large inductance, you can basically fake this 4 pi states in the system. So this is something we have to revise all our measurements. But okay, so luckily the number of inductance is pretty large in the system, which is usually not the case in most of the device people make. So that's still on the okay side.
But can you explain in simple words why small inductance mimic the 4 pi?
Not the small, the big.
The big one.
Mimic
the 4 pi.
I think this is related. Okay, it's purely RSCJ model, and you have this large L included, and you tune so much your potential, and then they start to allow them to have this pi stable.
So in general, any mechanism that helps you to do Landau-Zinner here, it's a general statement. So here you can have Landau-Zinner when you evolve with phase. So any mechanism that helps you to do this Landau-Zinner will mimic this crossing, right?
Yes.
So it can be inductance in the shunted junction. It can be quasi-particle coupling to the
Also, very high transparency.
High transparency, anything like this.
Yes, exactly. Another way or argument people put to exclude this Landau-Zinner transition is by doing this frequency. Because if you increase the frequency, you kind of help this process to exactly. So that's very commonly also, if you do this measurement, you come with another plot which shows that the increase in the frequency actually kill this fractional Shapiro steps. And I think for the moment, not that many systems show this suppression of the odd steps in a second or higher order. Many reports at the beginning only show the suppression of the first, but then they give even more, alternative explanations. So nowadays this is already like a little bit improved way of showing the 4 pi. And in this experiment, okay, I didn't even talk about what we measure, but okay, it's the business antimony with very little doping. So basically, it's a little bit like a direct system, but they have this high order topology, which states that's the playground. And I think here, well, we made a small improvement. I would say again, it's not qualitative step, but it's a small improvement in the measurement is that we show there are a correlation between the percentage or the presence of the edge states with this signal, 4 pi signal. So the more edge states we have, the better fractional Shapiro step result. So this is different, also reproducible because these are different samples. And to some extent also the temperature. By increasing the temperature, it helps to see stronger edge states because the
resistance of the junctions changed too, or is the same?
The resistance of the junction change as
mentioned. When you increase the edge states, the junction.
Well, they change a bit, I think. Yeah, for sure, because the number of channels.
You know, if you do not completely voltage bias, but current bias, so it's very difficult to know whether or not high frequency you provide only a current bias or a voltage. It change quite a lot the response of your steps, because I mean, it's changed the way that describe the RSG model.
Yeah, we don't fix any frequency. We always probe the maximum frequency or something accordingly to different devices. So you can see this like normalized estimation. So it's not we fix something frequency and you measure the same voltage, and then of course everything will be shifted. But this is already kind of normalized to the maximum frequency issue. Maybe this helps a little bit to talk in this context. Okay, so that's it. I think that's the thing I want to show. And then my point is, in this type of device, I think it's now pretty limited. In a Josephson device is limited. There, you can always make a better Shapiro steps, but still, you cannot say it's must be my topological signals. We have to move on, I think, to the other method, including this parity measurement. And this is from topological material approach, but that doesn't really prevent us from doing a similar kind of parity measurement or the correlation measurement. So I think that might be the direction to evolve. Okay, thank you.
So maybe Edgar, would you like to?
Yeah, always skip it because again, it's not topological what I'm going to show.
Yeah, but it looks like.
Okay. Yeah, so it is again the same disclaimer. Elaine asked to provide something or to explain where we were involved somehow, and that might have something to do with topology. And you see, well, this is an experiment from Eduardo Lee's group. And you see my name is here, so I'm author number 7 out of 11. So I'm the most innocent person in the game. And the only thing that we provided is sample fabrication. And what the system under study is a Josephson junction where the weak link is formed by an antiferromagnetic insulator. And well, this is how the devices look like, typical thing. And the most important findings are that one sees these squid-like oscillations, as have been observed in other systems, for instance, in the bismuth, in Elaine's group, and we also saw this morning. And then they did a very comprehensive study of angular dependence, and also here their oscillation. Excuse me?
B is in plane.
Is in plane. Yeah. And the periodicity also fits more or less to the cross section. When you assume the thickness is 10 to 20 nanometers, you assume some penetration depth or so, and you saw the shape of the sample, the cross section. So it's not always an easy geometry, right? But order of magnitude fits to the oscillation period. And as you see, they're also not always very equidistant. And also they may vary upon increasing the magnetic field, but they survive until very large magnetic fields, and then you can follow them by an angular study, and you make cross sections perpendicular to the periodicity or parallel. So, and this all let's say the model that has been put forward to describe it is by Ruben Suano, and that, let's say, the same arguments as we had that Chuan gave this morning, that there might be transport through edge states. And now the question is, where do the edge states come from? And here the model is that, as I said, this is an antiferromagnetic insulator, but at the edges there might be uncompensated magnetic moments. And then what women studied was how the energy landscape develops if one increases the magnetization, so the remaining magnetization due to the uncompensated moments, and then you see that the gap fills, and it may also come to a zero bias energy. And yeah, this let's say the way how to visualize then what it gives is in this plot here. So what is plotted is this weighted density of states, which is weighted by the energy difference to the Fermi energy, with the argument that states which are really close to the Fermi energy, they most have a high probability to give then also conduction channels. And then the idea is that, well, we have these two interfaces between the bottom superconductor and the NIPS, and then between the NIPS and the upper one. And there might be a situation that in both interfaces they are spatially close together, and then they could form a conductive state. And then there are also analysis on the temperature dependence and so on, which suggests that there might be edge states with a width of the order of 40 nanometers or so, but this is not a topological model. So it's just by coincidence that there are edge states, but it's not topologically protected. So this is in short the story that I wanted to share. Is there another slide? No, I don't think so. Ah, okay, yeah, this would be more details about the model, but I think we would skip it in view of the time. This is a bit visualization of what I just said in words. Okay, then.
Are there some comments also on your systems which presents this kind of protected states?
Also in the order 20 to 30 nanometers. Okay. So it's not single layer, it's few layers. Few layers, yeah. So and there, let's say statistically, I think I had a bit of statistics. So altogether, I think roughly 100 samples were done. 10 of them really show superconductivity to some respect. 5 out of these 10 samples who showed superconductivity show really Josephson junctions. The other ones had superconductivity in one or the other junction, but not really supercurrent going through.
And the AB plane, the AB axis are oriented in the same direction for the two niobium dissonant layer, because it has a threefold symmetry.
This we don't know. So you see they are stacked on top of each other, and so the in-plane orientation we do not control. We cannot really say. And I think this also gives rise to the, let's say, to statistics that only, this is what I wanted to say now, only 2 out of these samples which showed superconductivity showed this squid behavior, and others showed indications of Fraunhofer pattern corresponding to a very, very small cross-section, and so one was stuck in the first lobe, so to say. So this is our understanding of it.
You mean the robustness at high field related to the presence of squid-like oscillation? Because suppose you have more edge states in your system, like step edges and things like that, you may survive up to very high magnetic field. I mean, the critical current may survive up to very high magnetic field, but you cannot detect clear oscillations.
Yeah.
Because you have interference between many, if instead of 2, you take 3 or 10, or you can have a critical current which is very robust with magnetic field, but it doesn't show clear oscillations.
Yeah, this also may happen, right? So
you have seen this.
Yeah, let's say we had a question also by a referee about that, and I think we have examples where we can show we have 1. We have 2, yes. and there are also these fluctuating things, or no clear oscillations or varying oscillations, and we cannot really give a modeling what would be the geometry, because we do not control the geometry sufficiently enough.
Don't know how many
exactly
contact,
exactly
how you will contact.
Exactly.
That's another issue. Yeah. Now, so that's why my question is: even if you even in that case when you don't see the oscillations, do you have resistance of your critical current up to very high field?
Yes. Probably not as much as that, probably not up to 6 Tesla, but 2 Tesla or 3 Tesla.
Okay, more than what you would expect.
Yes.
Yes. This may be easy to explain, and for me it doesn't. It's not really against topological character of these edge states. It's just showing the fact that the contact. This is due to the way you contact to them.
Yeah, so what I want to say is we have no proof that it's topological. The model does not require that it's topological.
Yeah, but maybe you could measure something else. Well, did you try to measure current phase variation, for example? Or did you try to make spectroscopy of unrest states? Like human, there may be other ways to have access.
In these samples, this is what has been measured.
Okay.
And as I said, it's not my project. It was measured in Eduardo's lab. We were providing the samples, and let's say it's also the lifetime of the samples is not so high. So we could not perform all experiments that we wanted to have.
What is special about these NIPs? Why did you choose this material?
Because it's an antiferromagnetic insulator. So we wanted to probe an antiferromagnet instead of a ferromagnet to have in principle, no net magnetization that could kill us. And we wanted to have an insulator, and then you go through the palette of Van der Waals materials, and then you find this. There are probably 2 or 3 others, but this is the one that then works. We tried different materials, and we also tried materials that were grown in home labs. And at the end, what worked is the SNPs that we could buy from HQ Graphene. All the other samples didn't work. This is the history of the story.
But the edge state, you can also imagine that you have a different on the edge of your junction. The tunnel resistance is different, so you have a magnetic current through the edge of your junction. This is not exactly equivalent to have an edge state at some. So you may have simply the fact that the spins, for example, so your insulator is different at the edge of your
yeah, that's
junction.
what I'm saying. So it's an uncompensated magnetic moment.
Yeah, so this is quite different from the edge state of a system in which you couple the state of a high order topological insulator.
Yeah. This is what I said. It's a different kind of edge. It's a state that occurs at the edges, and there are reasons why it occurs at the edges because there's the uncompensated, let's say, mechanism, but it has a different origin. But nevertheless, it's an edge state. So if this mechanism works, it can only work at the edge. This is why it's called edge.
So many surface states or edge states which are not topological.
Yeah, exactly.
No, it was just trying to understand.
So we'll continue with the question.
No, okay. Now I think I don't know. What I would like, because we have only 20 minutes left. So Jean-Noël prepared something that I consider very interesting. This is the Carrel superconductivity in molecular graphene, where you have coexistence between orbital magnetization and superconductivity. So let me come to that. Oui, mais c'est pas grave, je travaille en ligne. Bon, à part que je ne mets pas, ça va comme ça? T'aurais voulu que je le
No, it's fine. It's fine.
Non, mais je peux le faire.
It's another example of a talk given by a theoretician about experimental work.
But
With a reference. So I want to discuss these 2 experiments. Actually, it's Hélène who gave me the papers. But it's very interesting. It's recent stuff about graphene. It's another variation around graphene. It's not monolayer. It's not bilayer. It's not twisted graphene. It's not about moirés. It's about this new kind of stacking rhombohedral, which is ABC, etc. stacking. And the trick there is that it's crystalline, but the band structure becomes very flat when you have like 4, 5, 6 layers. So there are several experiments here. I will talk about these 2 experiments. this one that says that they have signature of chiral superconductivity. And this further experiment in which they characterize the orbital magnetism in samples that are either superconducting or normal. So yeah, maybe that's the summary. I will start with this and then I'll show you the experiment. So I'll mainly discuss cases with 4 or 5 layers with this rhombohedral stacking. The experiments, they have mainly 4 knobs. They control the displacement field that allows to tune the band structure, like open gaps make the bands flatter. They control independently the electron doping, and they play with the perpendicular and the parallel magnetic fields. And what they find in many of these samples is that at high displacement field, when the band structure is really flat, and when they have a low electron doping and the electrons are all in the bottom of this very flat band, then they expect strong correlation, and what they see is interaction-induced spin and valley polarization. So let's assume that we are discussing at a level where we don't make really the difference with standard graphene. We have 2 spin flavors and we have K and K prime value. So due to interaction, you can polarize, only have 1 spin and only 1 valley that is populated. If you are in the normal phase, they call this a quarter metal because it's only 1/4 of the internal flavors that are populated. It spontaneously breaks time reversal symmetry because you no longer have compensation between valleys and spin. Therefore, in the normal state, it can show anomalous Hall effect, so Hall effect in the absence of an applied magnetic field. It also shows magnetic hysteresis. And in some of the samples, they see this quarter metal phase at low temperature, 300 or 400 millicade, becomes superconducting. And they still see that it breaks time reversal symmetry. And that's what they call a chiral superconductor. So it's superconductor that breaks time reversal symmetry. They also expect that because they think it's intra-valley and same spin pairing, because you're in a quarter metal, that because of Pauli blocking, you must have odd angular momentum. So they have no idea of the real symmetry, but they expect it could be P or F. And also because it's happening in a single valley, then they say it's Cooper pair carry overall momentum. So it should be some kind of FFLO type of superconductor. I want to make one point, I'll insist a little bit on that. It's chiral because it breaks time reversal symmetry, but they didn't check about topology. And of course, you can have systems that break time reversal symmetry, but that are not topological in the sense that they do not carry a topological number like a Chern number. I'll show you an example in a band insulator, which is well known, where you break time reversal symmetry, but you're not in the topological phase. Also in this system,
why is chiral?
Chiral in the sense that it breaks time reversal symmetry.
So PX is also valid. No.
So maybe the example that you're familiar with in the context of band insulator is this Haldane model.
Yeah.
So Haldane model, the phase diagram where you break either time reversal symmetry in the horizontal direction or inversion symmetry here. You can be in the nu equals 0 phase, but still you're breaking time reversal symmetry. So it's not enough to break time reversal symmetry.
You break time.
This is why I'm.
Chiral, you just break time reversal symmetry.
Okay.
That's
No,
the
there are several definitions of chiral.
that's
I already mean that you have
If
some.
you're a magnet,
This is skinny.
if you're a magnet, you also have
Because of DNA, it's different.
chiral in their meaning just means broken time reversal.
If you have an antiferromagnet, it's not chiral, but you still break timers.
It's also chiral in the sense that if you make the mirror image, you have the antiferromagnet in which you reverse the
Chiral means that this is different.
Yeah, but
Yeah.
okay, I'm just using the language of these guys.
Chemistry.
Yeah, this does not break time.
Yeah, but okay. Yeah, but that's
Okay, here
several
So that breaks time reversal symmetry both in the normal state and the superconducting states. Well, that's
and they also see signature, therefore, of orbital ferromagnetism. So it's a ferromagnet, but not because of spin, but because of spontaneous valley imbalance and the fact that in this kind of band structure, because of Berry type effect, interband, you have some Berry curvature and also what's known as orbital magnetic moment, which is not very different from Berry curvature, that exist in each valley, and usually they compensate because the two valleys are equally populated. But if you have population imbalance, then you can have this type of magnetism that appear. Okay. Now let me show you a bit about the experiment. So that's a schematic. They have several layers. They can do between 3 and 13, I think they've done. They back gate and top gate. They have also boron nitride just to encapsulate, but it's not aligned at all. And they have especially a very big angle to make sure there are no moires and stuff like this. And then they control the doping and they control the displacement field. And then they make this kind of maps. That's RXX as a function of displacement field and doping. And they find several regions with vanishing resistance, which they give different names because they interpret this as being different kind of superconductivity. So they have different signatures. If they do the experiment there or there, it's not exactly the same kind of superconductivity. Here you also have an example of what the displacement field does on the bottom of the band that is populated. So for this optimal displacement, the band is very flat, and with a small number of electrons, they are all in this almost flat band. You also see here a behavior as a function of temperature. That's for 4 layers, that's for 5 layers.
And so this is also the difference between C and D, 4 layers and 5 layers? No. What is the difference between panel C and D?
Yes,
okay.
Yes, this one is 5 layers,
and
this one is 4 layers.
Okay, now I see.
Okay, so now this was from the first paper, this paper. Now I'm moving to the one where they do magnetometry by a nanosquid on a tip. So that's again a map in displacement field and doping, but now they measure what they call the fringe magnetic field, and I'm not sure that I understand what it means.
Fringes.
Okay, but I understand it's proportional to the magnetization.
We measure also for graphene.
It's the stray field.
We call this stray field, but apparently we should call this fringe field.
Okay. Okay, and what they see is that this field, which is a measure of magnetization, spontaneous magnetization, it evolves as a function of doping, and you see it's almost 0, a bit negative, and then it becomes very big at some finite doping. This is in the normal state in the quarter metal. And the interpretation is that that's the band structure. They show it for 6 layers, 13 layers. And if you would draw the Dirac cone of a monolayer of graphene, you would see that it's very, it has a very large velocity compared to that. That's first, it looks parabolic, but also it's very flattish compared to the Dirac cone. And also what they see here is a plot of, it's not Berry curvature, but it's a related quantity called orbital magnetic moment coming from self-rotation. And they see a region around the K valley, a ring where this orbital magnetic moment is very large.
Simulation.
It's a calculation. Yeah, but this one as well. Yeah, sorry. These two are experiment. The bottom part is calculation. Yeah, I remind you about orbital magnetization computed in the Berry-like quantities. It has 2 contributions. One is this self-rotation or orbital magnetic moment. The other is this Berry curvature. And you need to populate all the bands that are populated. And here you have a Fermi factor, and here you have primitive of this Fermi factor. These 2 terms, you can imagine they are not that different, but they all come from interband effect. If you have bands that are not coupled, all these terms are 0. And so here, the spontaneous magnetization is only due to orbits. You forget about spin, you are in a quarter metal, you are spin polarized. Here you have calculation about the magnitude of these different contribution, self-rotation, and this center of mass orbital magnetization as a function of doping.
Sorry, if you spin polarized, you also have your big moment due to spin. If you
have only.
Yeah, but it doesn't depend on anything.
Yes,
Yeah,
yeah,
but
yeah.
still, yeah.
It's there, but it's not tuned by the.
moment of this is much bigger. You know, the Berry curvature gives you not μb, but it can be up to 100 μb.
Yeah, maybe it's apparent here. I didn't pay attention, but you see here it's 20 or 30 μb. And in graphene, the G factor is almost the one of it's 2, like in vacuum for the.
So it would be 1.
So it's very much more than the spin contribution. So that's in the normal state. But they also see these kind of things in the superconductive state. And this is my last slide. I want to mention this because I remember Hélène telling me about this and I didn't understand anything. So now I read it in detail. I understand a little better. They have something which is really weird, is that they can have a magnet in which, so you imagine you prepare your magnet, it's aligned with your external field in the direction of the external field. And now you tune this orbital magnetic moment by changing the doping. And when you tune it, there is a value at which the orbital magnetic moment, it reverses sign. And then it's anti-aligned with your external magnetic field and it stays there. It's metastable. And at some point it switches. So that's what's shown here. Here you're aligned. And here you change sign. I'm following the blue curve. So here I'm metastable, and suddenly it realizes that there is a preferred valley, but so here it reverses. So you have this effect, and this effect apparently you cannot do with a spin. It's only with an orbital magnetic moment. I don't know why.
It's not completely true. Apparently, you have also first order in certain quantum spin system. But you're not going to do that with the chemical. For example, I found paper on MOS. This is only spins. They have also, but this is because you have a first order transition. Yeah. But this is interesting because it means that if you have a first order magnetic transition, which means that you have a sea of paramagnetic spins, and in the middle of the sea, you may have drops of magnetic moments. Okay. And the physics, for me, the physics of first order magnetic transition is very interesting because we're not used to that. We're used to ferromagnet with diverging susceptibility and so on. You have something completely different here.
So that is the hysteretic. It's first order, so it must be. You're stuck in a metaphysical state.
Here, it's interesting versus temperature. This one. Here we have the problem is that
scan NE, so it's scan up and down.
So here what they show is that this double well is supposed to represent the two valleys, K and K prime. And here you first populate the favorable valley, the valley that's pointing in the same direction as the magnetic field. But then as you tune the chemical potential, the band structure.
So this is what they show. The blue is the way up and the red is the way down.
Yes, then it's unstable, but it stays for a while and then suddenly you realize.
But what's amazing is as a control chemical potential, not as a function of magnetic field.
Okay. Yeah. It's because this knob, it's also changing the band structure, and at some point the band structure, it switches the sign of the magnetic field. So maybe I will finish just with this conclusion that.
Yeah, but maybe you can show that you have this magnetic moment exists also in the superconducting.
Yes. So all this they expect. Indeed, the effect is bigger in the normal phase, but apparently it also exists in the superconducting phase. So at the moment they have a lot of signal that they have superconductor that breaks spontaneously time reversal, but they have no other signatures that it could be also topological superconductors.
Are they not the whole superconducting? And then what one sees in superconducting is it just the remainder of the normal?
No, I think they see a lot of physics related to domains. That's what they show here. So they have magnetic domains, but apparently the whole sample switches superconducting. Okay. But because of domains, you may see some resistance. because of the domain was.
I mean, you measure resistance, and it's enough that you have a path, a topographic path. It could be that if you measure these fringe fields, they are local.
Yeah, I was also, but maybe that's usual. But when I was a kid in school, they told me if you want to claim superconductivity, you should check for the Meissner effect, but nobody cares for the Meissner effect. Here I have the impression.
Even on local scale.
But maybe we didn't comment so much about pole resistance, because there was some question about topology, and the whole resistance is maybe not in this particular experiment, but people found that it is quantized, and very well quantized, in fact, in this because
apparently the normal phase?
You need to know what is tricky. I'm not sure I understand why. You need to align with one of the HBM, and then if you do that, apparently you have nice quantization of the whole effect.
In the normal phase.
In the normal case, yeah. I'm not sure. Okay, that's
and even without magnetic field.
Yeah, that's the point. This is the quantum anomalous. But you see, in order to see quantization, you apply magnetic field because you have a nice hysteresis cycle on the whole resistance.
The valley has a topological charge.
Which is the square of H, or which can be fractional.
Yeah,
if you have multi-layers, it can be fractional.
Yeah.
But here in the normal state, it's a quarter metal, so it's not an insulator, so it's not quantized anomalous Hall effect.
Yeah.
It's anomalous Hall effect, but not quantized.
Yeah, but I think apparently there is a trick in order to favor this quantum anomalous Hall, and maybe to it's a different region of the
because here I think they precise that indeed it's not they don't align at all with the HBN.
And also to stabilize this quantization, there is a trick putting a layer of tungsten dithyride, which creates some Ising spin orbit in the system. Maybe okay, there are some ideas that then you suppress spin fluctuations. I don't know. But okay, it depends what one. For me, the most interesting, I would say, is the magnetic phase. And this is quite robust.
This nice. What makes the shape of this wonderful socket here? The socket. Have a socket.
It's disorder, right?
It's the outer sample of the shape of the sample.
Is the shape of the sample.
Look on the.
And then you have something here, then you have something more here.
Now, apparently, there are domains in the contact. So it depends on the shape.
So
these two pictures that correspond to these 2 points, where this one is well aligned with the external field, it's this one is anti-aligned.
And then, but here you have some island too.
Yes, look at the sample. No, there are no islands.
No island in the sample. So you have a socket, but no island. Yes.
Okay, I think we have to read that paper, right?
Yeah, we can't do this.
There's a lot of things to
there are many things to understand. That's the point. And it's a complicated system, but this combination of fractional churn insulator and superconductivity is extremely interesting.
Yes. No, but here,
not here. There are other experiments
devices.
other devices which see fractional churn insulator without application of magnetic field, and they see superconductivity somewhere. So the experiment in China.
Yes, there is a Chinese group who presents data.
These are very consistent, so it's homohedral and not this twisted.
Yeah, so I think the fact, but the homohedral looks to be, but the problem is that fabrication is also some issue because you can fabricate a bundle again it's homohedral. So then it can self-anneal and then it will be burned.
Yes, 30 layers of PVC.
Wow.
It happened on its own. Problems that
I
never
don't
not
know.
with
They don't
ABA.
make them. They don't
Yeah.
So you find them somewhere in your graphite, and it's metastable region, right? If you admit it, it becomes Bernal step.
What's a very long metastable? The very long metastable because it requires shifting the entire layer.
You can find it. It's metastable.
Yeah, I mean, it is, yeah.
But it's not stable. You needed it all that way.
But you need
Everything had to be done before this environment.
Not so cool, but you know, the problem is processing. You want the software.
Maybe it's 30% not ABA, it could be ABC.
Yeah, it's ABC.
No, but I'm not sure.
No, we can continue.
Yeah. So I don't know,
Maybe to conclude, you could propose the key experiment. I have the impression that one or two came out from discussion, just to triple, quadruple check that there is a topological state. So we know that zero bias peak is not good enough, that zero bias peak that doesn't move with certain parameter is not good enough, that Fano factor can exclude most of, but is not good enough either. So what's the conclusion? What would be the experiment you would propose?
Correlations.
Robustness.
Correlation, but no, the experiment essentially was done on these small qubits, but for very large, they are very robust. And you change things, and they
correlation on large qubit.
So no, this is the qubit experiment.
So that they are.
The ideas were not by tapping Majoranas, but by measuring them, which is measuring their state. So this whole idea of doing computation by measuring.
Then you still demonstrate the braiding or this kind of thing.
That's the next step. But this one we won't be the first step.
Maybe there is a system that is interesting, annovatoring, that was in LPS several times, shown that when you take just a single atomic layer of tin on silicon doped, you start with a mode insulator, and then you dope your mode insulator, it becomes a metal. This is a particle peak. And they could induce superconductivity with a pretty ITC in it, I think something like 10 Kelvin. And they got some Shiba states even for vacancies or for normative effects. And also they observe some edge state at step edges. So there is a clear signature of spontaneous chiral, so probably D wave, D plus ID. It's difficult to prove, but chiral for sure. So it means that we have at least one system in which is super clean with a fully open gap, with a hard gap, with a very high TC that could be of interest. The only problem is that it's something that you have to grow in UHB. So if we could stabilize this by doing some depositing some overlayer in order to protect, and then give this to people that could do some electronlithography on this system, it could be interesting. I think it would be worth trying to reproduce this work of Vitering. Is asking us, we have this anno Vitering. The guy, he was there. Yeah. So I think it would be important to reproduce this, because maybe this is the route towards at least 2D chiral superconductivity with a large gap. So it's good for prediction of the edge states and everything. So maybe we should try to find a way to extract this from UHV and being able to have this sample stable in air with some kind of capping layer, and then irrigate all the community.
Can you repeat which material was it?
It's a tin on silicon.
Tin on silicon, okay.
PDOP.
If you want to conclude?
I don't. Okay, what should I say? I don't know. I didn't prepare any.
Thank all the.
Okay,
Yeah, thank you.